So my name is Alex Powell. I'm a research fellow. Ooh, it's gone rogue. I'm a research fellow at the University of Exeter, working in the Centre for Metamaterial Research and Innovation. And I'm going to present to you today some work on metamaterials and my research on using them for compact antennas and increasing radar visibility of small objects. So just before I go any further, for those of you who have never heard of what a metamaterial is, it's a material that's been engineered to have properties that aren't usually found in nature. And generally, we're talking more specifically about how materials interact with waves. And so we can make them interact with waves, be them acoustic or electromagnetic, in ways that's not usually possible. And I'll go more into this in a second. So in this talk, I'm going to first introduce Exeter and the institute we have there very briefly. I'm going to talk about metamaterials in a bit more detail and some of the headline grabbing news that's been happening over the last 10 years in metamaterials. And then I'm going to go into my work on smaller and more directive antennas and making small objects visible to radar. So you might have seen from this talk already that the sort of TRL level is much lower than what the majority of talks in this conference have been. And I seem to have gone through an automatic scrolling thing here, which is annoying, but hopefully that won't be too disruptive. So yeah, the TRL is much lower. We're a scientific research institute, but we do work very closely with industrial partners. And my aim for this talk is to kind of introduce everyone to metamaterials and some of the work we're doing at Exeter. And I think there'll be certainly some areas of overlapping interest. And I hope this will spark some future discussions with anyone who's interested further down the line and maybe working together at some point in the future. So to introduce Exeter University is about as far away from Glasgow as you can get in the UK, but we are the home to the Centre for Metamaterial Research and Innovation. We have over 100 researchers looking at various different aspects of metamaterials, and we've just been made the lead institution around Professor Alistair Hibbins and the new UK Metamaterials Network, which is an effort that's bringing together dozens of research institutes and industrial partners throughout the UK and beyond to try and build metamaterials capability in the UK. And we research all kinds of aspects related to metamaterials. We research things like acoustics, fluidics. We've got quantum stuff based around 2D materials like graphene, and anything to do with electromagnetic radiation. So from the visible to the terahertz to microwave and radio frequencies. And we kind of put all this together to do some really cutting edge, interesting science, but also to work with industrial partners. So we have collaborations based around improving solar cells, around new diagnostic techniques for health, lots of defense and security stuff, and maybe in the future, some space stuff. So I'm going to introduce a bit more about metamaterials themselves, give you more of an idea of where we're coming from. So as I said, the materials engineered to have properties not found generally in nature. So the way that a normal material, any material, interacts with like a wave, so a light wave, say, depends on the atoms it's made out of and the way those atoms are organized. And so if you have, light hitting a piece of glass, the atoms vibrate and dictate how the light passes through the glass and what's reflected and all of that. So we can look at every atom, but usually what we do is we consider the material has a bulk property. So we say, okay, this material will do this, but actually it's dependent on the behavior of these individual atoms kind of combined. But we can say it's a bulk property because they're so small compared to the wavelength of the light we're looking at. And so we can do the same with metamaterials. We're doing exactly the same thing, but we make each constituent part. So we make these small meta atoms where we control. And there's a few examples you can see. Each of these materials in the bottom here is made up of individual little particles. We can control their properties, we can control their ordering, and so we can give these kind of extended surfaces and 3D materials based around these meta atoms. We can give these bulk properties they'd never be able to have normally, which can lead to some really cool stuff. And going beyond this, because we are making every single constituent meta atom, we don't have to make them all the same. we can make each one slightly different from its neighbors. And because the properties of each atom determine how they interact with radiation, if we make each one slightly differently, we can make radiation bend in all kinds of weird ways as it passes through the material. This has been used to achieve some really cool stuff. Like one of the most famous experiments is shown in the top right, and this is designing a cloaking device for microwave radiation. So you can if you put a metal object in the middle of this kind of cylinder made up of these layers of metamaterial, then you just won't be able to see it by shining radiation on it. You'll see absolutely nothing. The radiation just bends around because the material has been structured in a very clever way. And we can also achieve flat lenses from this way. So normally a lens works by changing the path length from a lower refractive index material to a higher refractive index material. And this is done by changing the thickness of a lens. But because in a metamaterial, we can change the properties each point of a layer or a 3D material. We don't have to change the thickness. We can just change the path length by changing the optical properties. And so we can make flat lenses, or even lenses based on surface waves, which can obviously save a lot of weight and can be very compact and can be easily integrated into all kinds of structures. So there's a big future for metamaterials in that aspect. So that's just to give kind of an introduction to the field for those of you that haven't heard of metamaterials before, and to have some of the kind of headline grabbing innovations introduced to you all. I'm now going to go into some of my research, which is about two main fields. One is making antennas smaller and more directive, and this is largely based on transferring from using electric coupling of antennas and ground planes to using magnetic coupling. And there's two approaches I'm going to discuss for that. And then some more recent work, which is a bit more in the scientific stage at the minute, which is improving radar visibility of small objects by creating some highly scattering 3D metaatoms and also looking at some transparent 2D metamaterial arrays. So one of the problems, which I think was actually touched on in the last talk with antennas, is often they have to be put near to bits of metal, often called a ground plane, but it's just a highly conductive surface. So anything metal in the microwave range, basically. And a normal conductor acts as an electric mirror. And this can be thought of as when radiation is impinging, is incident on a conductor, it will excite surface charges that are excited basically to oppose the electric field of the incident wave. And so what this results in is the fact that you have no net field at the very surface of the metal, and any radiation reflected from the metal is going to be out of phase with incident radiation. So the peaks and troughs of the electric field are going to be completely out of phase of each other. And what this means is that if you have an antenna next to a ground plane, that radiation directly emitted in the forward direction from the antenna is going to destructively interfere from radiation that's bouncing off the ground plane, which can be super annoying. And if you want to have constructive interference, your antenna is going to have to be a quarter wavelength away from this bit of metal. And sometimes this is fine, but if you're looking at longer wavelengths, this can be quite far. This can really limit the size of your antenna. It can be sort of 15 centimeters for the ultra high frequency band. So a way around this is to design what we call artificial magnetic conductors, which are also called high impedance surfaces. And an example of this, which was derived theoretically about 20 years ago and sort of in the last 10 years has been developed in our labs and some others, so by structuring this sort of mushroom-shaped surface, when radiation is incident upon the material, it doesn't excite sort of surface charges as we would normally see. It excites current loops, as can be seen in kind of the bottom illustrations, which is basically the magnetic equivalent of a surface charge, which is why we call it an artificial magnetic conductor. And the upshot of this is that when radiation is reflected from this surface, it doesn't have a phase shift in the way it would from a sheet of metal. There's no phase shift. You can have perfect reflection still, but no phase shift. So for an antenna, you can put your antenna right next to a ground plane made of these artificial magnetic conductors and still have constructive interference. So this is super useful for all kinds of systems. And we've actually just been finishing a 2-year collaboration with a company called Cobham, who are based in the UK, who had a contract with one of the major plane manufacturers, trying to make the radomes in planes more compact, because the radomes would typically stick out from the surface of the plane and create more drag. And if you could make it smaller, or even like inside the plane, then or flushed with the surface of the plane rather, then it would reduce drag and save fuel, and that would be great for everyone. And so we used an artificial magnetic conductor that we designed at Exeter to combine with these antennas going into planes, and managed to dramatically reduce the size of the radomes. And this project was basically really successful, and we're looking for further collaboration with them in the future. So this is just one example where these artificial magnetic conductors are becoming useful for industrial purposes. I'm sure there are going to be lots more examples in the future. So that's one way of making antennas smaller, when they have to be next to a ground plane. Another approach is to look at everyone's old friend, the Yagi-Uda antenna, which is basically composed of an emitter dipole and a reflector dipole, and then some directed dipoles. So the emitter is driven, and everything else is kind of driven by the emitter, and you have various interfering reflections and transmissions from each dipole element here. And to get strong directionality in one direction, there is an optimum distance that each element has to be from each other, which is determined only by the wavelength of radiation you're looking at. And this is all maths that was established back in the 60s, and this is pretty well-known stuff. So there's a limit to how small you can make these anyway. So we're looking at ways to make these antennas smaller, and actually you can couple just using normal radiation in free space, but you don't have to do that. If you have elements that have a strong magnetic component, so anything with a circulating current will have a magnetic component, so these split rings at the top, and then these helixes further down are even more powerful magnetically, you can actually couple magnetically instead of electrically. And the effective wavelength between magnetic coupling is much shorter than the wavelength of electric coupling. And so what we found is, by having basically starting to build a Yagi-Uda antenna out of these coil structures rather than just dipoles, you can reduce the height of your element by a factor of about 10, sorry, and you can reduce the separation between them by a factor of about 3. And this is before we start adding any high permittivity fillers or anything. So in an unoptimized system, we've already had significant reductions in the size of this antenna. We've just published a work based on just a driven element and a reflector, and we're going to start moving on to looking at more directional elements and seeing how far we can push this. So those are two structures looking at making antennas smaller, which is a big part of our work. The other part, which is slightly newer, is starting to look at structures that are highly scattering for radar signals. And we have two approaches to that. One is to try and recreate the high scattering properties of metallic nanoparticles in the optical regime. And so we can kind of create the very powerful resonances and concentrated electric fields around these particles by structuring these 3D shapes in very specific ways. And basically, we create a very strong electric field around these shapes at a specific resonance wavelength, resonance frequency. And this electric field extends into space and makes the particle kind of appear much bigger than it is to incoming radiation. So it scatters light very effectively. And we can achieve dipolar modes and also more exotic modes like quadrupoles and magnetic families of modes also. So there's a lot of interesting fundamental physics here, but they're also very bright radar scatterers. So we're looking to find some more applied uses for these as well. So I'll skip through because I'm getting close to the end of this time. But just to say, we've done some initial experiments with 3D printing these, and they've worked very well. And the final application I want to talk about also relates to some things in the last talk, trying to build, in this case, retroreflective arrays. So this is based on a Van Atter array, which is a pretty well-established mathematically method to achieve retroreflection from a 2D plane. And essentially, you just have a bunch of antennas which are connected by transmission lines of equal length, and you have them in a row. And so when a wave hits one antenna, it's through the transmission line, it connects to its opposite number, which then emits, and this goes down the line. And so the order of emission is opposite from the order of transmission, and it means that the reflected wave is always going to be exactly in the direction it came from, which makes it a retroreflector. And these can be really compact and lightweight and very effective over quite a large angular range. So one thing we're looking at, which is kind of the new spin, is to work with a company in America that's, well, we're in discussions with a company in America about producing these using an optically transparent conductor. And this is kind of a new model that has not really been used that much for this kind of thing in the literature, but it's very high transmission, much higher connectivity than most of the previous things that have been tried. And so it suffers less from kind of the problems of low conductivity than some of the older stuff. And the idea is we can make anything. You can make a lens, like metamaterial lens, like I've shown before. But in terms of satellites, we could make potentially one of these retroreflectors that could be transparent, but highly reflective back in the direction that radiations come from. So it could be used to be integrated with any of these chipsats or small pocket cubes to dramatically improve their radar visibility, maybe make the FCC a little bit less shirty about small satellites. So that's kind of work that's up and coming in our department. This brings us to the end of the talk. I hope I've been able to give you a little flavor of what's been going on in the world of metamaterials and the kind of work we're doing at Exeter. We're going to be pushing forward on all these fronts here. So making more of these artificial magnetic conductors, more compact magnetic antennas, and then the strongly scattering retroreflective radar stuff is also something we're going to be pushing forward with various collaborators. And I hope that some of this will be of interest to people in the satellites community. I'd love to start some conversations around ways we could work together in the future, or even just the kind of thing that the community is interested in to kind of help guide our research.